We are now on the last section of Chapter 8, Rotational Kinetic Energy. But before we get into that, just a few tips on solving problems in rotational dynamics. Make sure that you know that how to identify the system being discussed, draw a free body diagram using a rigid body process, find the axis of rotation, determine the torque around it, derive an equation applying the first condition, second condition, or the second law for first condition. If you don't know the inertia, then we're going to find that using this equation. You do not need to memorize the moment of inertia equation. They will give this to you in the problem if they will ask for you to solve or calculate. Use other laws and principles such as conservation of energy, angular acceleration, angular velocity, and other stuff that you've learned. And also don't forget to write the appropriate units. So let's move into kinetic energy in terms of rotational concept. So going back into our concept of linear motion, we know that if the object is in motion, then it must possess an energy. So in linear motion, kinetic energy is equal to mass times the velocity squared. So if the object is rotating about an axis and it's not slipping, so at one point there's static friction that will cause it to rotate, it is said to possess kinetic energy. So kinetic energy that is rotating is equal to 1/2 given the mass. So the mass for this rotational would be inertia, and then the velocity will be angular velocity. So we have the equation for rotational kinetic energy. So how simple is that, right? So let's apply this concept in terms of conservation of energy as well. So say for example we have an object at a certain height on an inclined plane at a certain angle. So let's find out. So this is a marble, so its rotational inertia, so its inertia for a sphere would be letter E, so it's 2/5 mr squared. So we're gonna use that in a little while. Okay, so given that it has gravitational potential energy, so the energy conservation concept applies here. Initial, final is conserved. So initial energy would be the height times the g times the mass. Since it's a rigid object, so it's going to be uppercase M to designate that it is the total mass of the rigid object. Y represents the h. Okay, and then we have kinetic energy, linear. So center of mass is where the velocity of the center of mass is, plus the moment of inertia, center of mass as well, and then the square of its angular speed. So if we're going to look into this, so we have, let me just write down velocity, just point out this is the center of mass given the moment of inertia for a sphere, so we can plug this out. So 2/5 mr squared. Knowing angular velocity is equal to velocity over r, we will have that squared, since that's squared, so we will replace that with this. So velocity squared over r squared. So we can factor out the mass and the radius. So we can cancel it out. And then we have gy is equal to 1/2 v squared. 1/2 times 2/5 is 1 fifth velocity squared. So we have 10 over 7 velocity squared gy. Solving for v, we have 10 over 7 gy. So that is how we find the velocity of the marble. Now let's compare this. Say we have another object, which is a box. Okay, so they are both going to undergo rotational motion, so they are not slipping. Okay, so this will have both rotational kinetic energy and translational kinetic energy. So applying the conservation of momentum, its energy will be converted into two types of energy. Now let's look at the box that will just slip. So this will only undergo translational energy. So the conversion from initial energy to the final energy will just be from potential to kinetic, 100%. So if we are going to find for the velocity of an object that's sliding, that is this box here, okay, going down an inclined plane, so we will find, if we go back, it's gonna be 2 gy, right? Therefore this one is greater than the marble. So the velocity of the box is greater than the velocity of the marble, given this equation. Therefore, who wins the race? It is the box. The box will have the fastest speed. So let's practice. Looking at this, which of this object will be the fastest? Which will be the slowest? So neglecting friction, and the objects are not slipping. So how are you gonna arrange this? Going back to this table as well. So you can use your textbook and plug in the relationships. The correct answer would be in the same order. So the fastest will be the box, followed by the marble, followed by a solid cylinder, followed by a hollow cylinder, followed by a hoop. The hoop will be the slowest. If you go back to all this equation. So the hoop has a greater moment of inertia. This one have the least. So a while ago I've mentioned about conservation of energy. So the object has a particular motion and as a mass, so we can also have an analogy in terms of linear momentum. So in terms of linear momentum, we can also have a rotational or angular momentum. So let's recall our equation for linear momentum, which is P is equal to mass times velocity. Now if we go back to rotation, the symbol for linear rotational momentum is uppercase L. So we could replace that for rotational, would be uppercase L, and mass related to inertia, and you know velocity is related to angular velocity. So you have that equation. If we say that the momentum is conserved, if momentum is conserved, so stays constant, if we want to see the relationship of the moment of inertia with angular speed, so if the momentum is conserved, we know that as the inertia increase, just like the ice skater. When it extends its arm, its moment of inertia increase, and what happens to the angular speed. So when this one goes up, this one will go down, and vice versa. So that's how we see a relationship on that. Another analogous relationship would be, is the work done by torque? So given in our linear work, so we have work is equal to force times the displacement. So in terms of our angular or rotational, so we have that change in length. We know that we could find the arc length as equal to the change in displacement times the radius. So we can plug that in there. And we know that work will be force, and we know that force in torque is equal to torque over radius from the equation force times the radius. So we could plug this in here over R, change displacement over R, so we can cancel that out. So we have work is equal to torque times displacement. That's our equation. So same unit for work as translational motion, which is in joules. So that's Newton meter. And then what about power? Since power is equal to work over change in time, since work is that, and then change in displacement over change in time. Does this look familiar again? So rotational power would be equal to torque times angular velocity. So what's the unit of power? It's still gonna be watts. And also this is the same as linear work. Power time is equal to force times the velocity. So you want to be more powerful, you're going to have a large force and a large velocity. So large torque, larger angular velocity, a more powerful object.